Hello, viewers. My name is Adam Pickerel. I'm here with Tyler Kramer, Lewis Parr, Connor Smith, and Grant Wilkins to talk about our Senior Design 2 project, sponsored by Dr. Raza and the Clemson ECE department. We wanted to create an automated drink dispensing system that we call BarBot. We created this to relieve stress from bartenders and create a compact robot that could cool mixers and containers, add alcohol, and create an output drink for any user that could order it from an application on their phone. The goals of our project were to create a GUI that we call Jarvis that would allow a device to talk to a Raspberry Pi microcontroller. This microcontroller will act as the main controller in our system and will control our pumps and other devices. The final deliverable will be a closed system implementation of a bartending robot that, upon order, can deliver a mixed cocktail drink to any user.
Project implementation. So this is basically our front end and our back end of our hardware. So looking on the left, this is our front end, which is where the bartender will interact with the overall system. We have 6 containers here, each containing mixers or alcohol. And we have our 7 submersible pumps here, 6 float switches, our travel pipe. We have our cleaning system. We have our 4 linear actuators. We have two 12-volt pumps and two 12-volt valves. So on the right here, we're looking at our back end of our hardware implementation. This is where all of the wiring and logic for our project is, and the user is not really going to interact with this.
Here we see the front end interface of our project, which shows the home menu. To go to the configuration menu, you click the red shown in the bottom left, and to go to the drink menu, click the button in the middle of the screen. The drink menu shows available drinks, and when clicked, they create a gRPC call to our Raspberry Pi controller. This also allows you to select a flavor like mint, lime, orange, or grapefruit to inject into your drink. And the configuration menu also shows the container levels for the current drinks in the system.
All right, so this is our system block diagram that we have. The Raspberry Pi is running all of our pumps. The pumps go through the travel tube into a dispensing and mixing tank, and then that is output. We have some other systems here. Our cleaning system right now is just represented by a bucket, and this would eventually represent an actual mains water system, and this would will just clean out our mixing container. We have syringes for different flavor injectors. This would be more concentrated flavors like lemon or lime. And then we have an STM32 running our float switches, which detect for low levels and will output beep codes on a chiming system. And our final dispensing system will actually detect if a cup is placed underneath the dispenser.
Here we're looking at our hardware design requirements, which is kind of the motivation of our overall design, which are things that we were really looking for when designing our system. So we're looking at less than 10% spillage. This is calculated by looking at the amount in the cup minus the amount pumped out. We're also looking for a quick exchange system to reduce refilling time, which was done by using two 12-way connectors. We also wanted to dispense a drink in less than 1 minute to make this system overall quick and easy for the bartender to use. We also wanted the no-load submersible pumps to dispense roughly 1 ounce per second. This was calculated using the calculations as seen at the bottom of the slide, which came out to be around 0.94 ounces per second, but obviously we have a load on our pump, so accounted for that loss.
Our hardware subsystems consisted of a control system that was a Raspberry Pi, a power system that was a 12-volt switch mode, and a 12 to 5-volt buck converter to supply our 5-volt technology. Our liquid containment was 6 1,500 milliliter containers, 6 float switches, and our cleaning system had a 12-volt pump and a 12-volt valve. Our dispensing system used the same 12-volt pump and another 12-volt valve. Our liquid mixing used a 5-volt submersible pump. Liquid pumping from the containers was using 6 5-volt submersible pumps, and then the flavor addition used 4 12-volt linear actuators and a L298 motor drive.
As seen in the slide, we have our hardware panel, which we're going to dive a little bit deeper into. So each component is listed along with its respective connections. This design uses a 12-volt power supply that supplies the power module, as seen in the slideshow. The components in the system either require 12 volts or 5 volts. In order to provide 5 volts, a 12 to 5 volt buck converter is used. The 12-volt supply inputs a buck converter, which outputs 5 volts. The 5 volts from the converter is also tied to the power module. The idea of the power module is to have a centralized access point so that each component can receive its required voltage. The Raspberry Pi in this project is utilized for its control capability using GPIO pins. 2 modules were created to centralize the GPIO pins for easy access. This is GPIO access 1 and GPIO access 2. Here, the pins from the Raspberry Pi are locked in using screw terminals. To easily access the GPIO pins, a row of screw terminals is soldered into place and connected to the row of screw terminals where the GPIO pins are inserted. On the output end of the GPIO access 1 and 2, different devices can be connected and controlled by the pins. The different devices that are connected to this module are 2 L298 dual channel motor drivers, 2 12-volt valves, 2 12-volt pumps, and 7 submersible pumps. The 7 submersible pumps are controlled by the 5-volt switching circuit module. Each submersible pump can be controlled individually with a GPIO control input to the 5-volt switching circuit module. The 2 12-volt valves and the 2 12-volt pumps are controlled by the 12-volt switching circuit module. Each device can also be individually controlled due to the GPIO control inputs. The 2 L298 dual channel motor drivers are directly connected to the GPIO access module. The L298 device is required to control the 4 linear actuators for flavor addition. A device called the STM32 is also used externally. This is another microcontroller used due to the limited GPIO pins offered by the Raspberry Pi 4 and functionality. This device is used for liquid level detection, which utilizes flow switches to indicate whether a container level is low or not. If a flow switch is no longer afloat due to a low liquid level in a container, it will switch closed and send a logic low signal to the STM32. Once the STM32 receives the signal, it will chime the timer circuit, and this will alert the bartender that a container needs to be refilled.
All right, so we'll be going over a little bit of the software design requirements that were needed for the BarBot, more specifically the Jarvis app that was used to interface with the BarBot. So as with any app, there's a front end and a back end. We'll go over the front end first and then go over to the back end. So on the front end, we would read and format these drink recipe data kernels so then they could be sent over to the device side by what are called gRPC calls. G is for Google, and RPC stands for Remote Procedure Call. We'll be talking a little bit more about this later. And so we also wanted to expose to an administrator the ability to change drink configurations, check the different container levels, and then also clean the system itself. This would allow a full control of all of the hardware that was available in a very secure way in the app. Also, we would then allow users to then order the drinks with the flavors that were provided via the syringes that were talked about earlier. And then we would also dynamically update the drink menu based on those available ingredients and also the container levels measuring liquid that had been poured. More specifically, we did this not empirically, but instead through calculations using the approximate flow rate that we had measured from all the containers and then subtracting how much had been ordered. So then moving on to the back end, we designed the gRPC client basically to interface with the front end very easily. So upon some button click, then there would be a callback function to the gRPC client that would then send a request to a busy waiting server on the Raspberry Pi end. So these different gRPC requests would pass the drink and flavor inside of one packet, that packet being less than 200 bytes. Very lightweight communication and very robust and easily defined data types. We would then also maintain a digital representation of the 6 containers, as we mentioned that we would dynamically update the container levels, and then we would enforce an approximate flow rate of 1 ounce per second, which was enforced through the request to the hardware, but then also enforced through, again, these dynamic container levels. Finally, we had the gRPC server then in a busy wait for client requests. So now moving in a little bit deeper on the software design. So again, as a reference, there was a GUI for the application, which was just covered. This would, upon a button push, send over data for a gRPC call. This gRPC call would then head over to the client, which would then wrap it into a gRPC packet, which would then emit it to the gRPC server. As we can see, the gRPC server gRPC server is in a busy wait. As you can see in the top right corner of the slide, it would receive an order for the different ingredients and then also receive flavor injection requests. Then this data would be sent over to the Raspberry Pi device code, which would then unwrap it and interpret it so that different pumps and GPIO pins could be activated, whether that be the actuator for the flavors or, as I said earlier, the pumps. Then finally, uh, the gRPC client would be hung waiting for an acknowledgement, and as would the GUI for the application, not moving on to the next screen until an acknowledgement was sent first back to the gRPC client, then that acknowledgement being passed into the GUI. And as you can see in the bottom left corner, the gRPC client is called from some request, so you can see how much was ordered of a specific ingredient and also the drink that was ordered itself. And moving a little into the methodology. So some of the things that we attempted to do to make our system more secure and also just to implement our system were the OpenSSL security model, which would have public and private key pairs so that a server would know to trust a client. However, instead of this, to make things a little bit simpler, we used a private wireless hotspot to secure communication so that the only way that you could place an order would be if you were joining this private wireless hotspot, which was secured by a randomly generated password every time it was activated. But most importantly, what we implemented throughout this entire project was the RPC theoretical model. This is common across distributed systems, as remote procedure calls are lightweight and easy ways for different devices and different processes to communicate with each other. In particular, we use gRPC. Google Remote Procedure Call allows for an easy way across all languages to define different remote procedure calls, and also a very lightweight way. And this was especially useful in early stages. We assumed we would be using different programming languages. However, as we moved towards Python, it was still much more simple than other remote procedure call libraries.
There's several challenges and bottlenecks that we faced. The Raspberry Pi GPIO pins are unpredictable. They'll randomly float sometimes if we don't set up the pins in a certain configuration. The distance sensors weren't inaccurate, our load cell was inaccurate, and we're unable to get SPI or one-wire communication to work consistently. The amperage of our power supply, our original power supply, wasn't adequate, so we switched to a 83 amp power supply, which is overkill, and then we convert that down with a buck converter that's rated for 3 amps. We had trouble compiling our app for a smartphone application, as it was trying to access restricted memory on one of the smartphones. Also, we're having issues with the float switches being sticky.
We will now show a demonstration of the flavor injection syringe and a full demo of our entire system. Thanks for watching.
I'm not gonna lie, that's the only reason I have it. I told myself, yeah. Oh, is that shoelaces? Actually, should wow. That one gets stuck in the belly. Yeah.